All right, so I did find, this is the CoinCap API. So they've got a little site here for getting data about cryptocurrency markets, essentially. They've got some pretty decent documentation here that says, hey, you can go through and send a request to this site here. Let me zoom in a little bit here. And then this is what you get back. So when we were talking about Json, which is essentially, it's a way for us to save data as a dictionary. Python does it relatively well, pretty quick here. So we get data, which gives us a list of another dictionary. And so we're going to get a bunch of information here. Here we go. It's a little easier to see. So this is the first item in the dictionary, or first item in the list, which is a dictionary. And it's here's the key, here's the associated value. Here's the key, the value, key value, right? We're familiar with these key value pairs. So we can send this information, we can get this information from the web API, and then we can do something with it back in Python. So this is going to be super common dealing with web APIs. So you can just send a request out to this assets here, and these are just GET requests here. So let me copy that and open up PyCharm. I think, do I have, I didn't do requests here. Let's do, sorry, sugar high? I didn't eat anything. Oh, low insulin, okay. All right, and we'll do a new one here. So here's just like miscellaneous. Come on, PyCharm. All right, so to do this, we need the requests library. So we're going to import requests. If I could spell it right, that would be helpful. Requests. Yes, requests. And then if you've never done it before, you have to go and install the package. So when we use these virtual environments, right, it makes like essentially a separate copy of Python for us. So if you have a virtual environment, you'll have to install the package every time. The idea is you don't always want to add all these other miscellaneous packages to your base Python install, just in case something weird happens, right? So it's a way to kind of protect our development environment here. So we're going to install the requests package, and it should just go get it here, which is pretty quick. You can do it all by hand if you want, but PyCharm takes care of all that hard stuff for us here. And then requests. You know, honestly, I just go look it up here. Yeah, so if you want to do it by hand, you can use the pip install tool. We never do it by hand because that's really tedious, but you can. So we're going to say, I want to get something from a given location here, and I get something back, right? So we'll just steal that, right? Why not? But I don't want to send it here, right? I'm going to send it out to my CoinCap API. So here's my little URL here. So we'll drop it in. When we deal with web stuff, you get all sorts of status codes. Eventually you'll learn more about this in networking or web classes and things, but 200 is the good one. 200 is success. Somebody picked it a long time ago. I don't know why, and that's okay. So we get all the code here, so we should just get some data back. Oh goodness. Oh, what did it tell us here? Requests. Oh, we broke it? Invalid URL, no scheme replied? V2 assets. Oh, I didn't give it the HTTPS. My bad. I have to tell it use HTTPS. That ought to work. Hey, all right, cool. And we get some data back. So we're able to get back what they showed us here, right? So it's able to work with this. So I can store all of this then as a dictionary, and I can go through and loop through all my items here. So this will be my data is equal to my response.text. And then, now, this one's a little bit silly here, right? It's a little easier to view over on this page here. Where's this? How did I get it big? View more, that's what I did. There's one item in the dictionary. That item is then the associated value is a list, right? So everything is really associated with this single item of data, right? It's just all a big list here. So it's a little silly. The only other piece we get other than data is the timestamp. It says, hey, here's when this data is from. So we get, here's data with everything inside of it, and then we get a little timestamp. But we should be able to get that out. So we can say for key in data, we can print the key. We should get our data and our timestamp. Oh, no. Oh, no. Shoot. That gave me every single item. And I think I want that as a dictionary. No. Oh, man. Sorry, one sec. Data is response.text. We have to turn it in to parse the JSON. That's right. So Python JSON dumps. Okay. Yeah, we got to import the JSON library. I was skipping ahead. So we import from the JSON library so we can work with JSON data directly here. And then we want to decode. Here we go. So I want to take some JSON data and I want to load it here. Right? So it loads. Should just be able to get my loads. This website is terrible here. I want better. JSON load. Okay, JSON load. Okay. JSON.load, and we're going to load the response text. Now we'll see if we get anything back out here. Loading. We got the data. String object is not trying to read. Load. We'll see what our first data is here. Oh, we can just get the JSON method back out. That's handy. Okay. JSON loads, yeah, the response text. Isn't that what we did? Our JSON data, unload, response text, string, response.json. Can we just do that? Response JSON. Okay. So if we know we get JSON back rather than just the text here, let's try that. Hey, okay. We found the right key here. So if we know it's JSON data, we can just get it directly, working with it. That's the trick for us here. Other silly things you can do, you can send it to other websites here. So if you really want here, where is it? I can take my page here, and this won't work for us here. Comment out for a second. But you can get any page you want, really. You drop it in here. And we can get data off any website, essentially. And here's the HTML. Right? This is the actual text response that we got back. So any website doesn't have to be an API, but imagine just going off to a website and then having to, okay, let me go find something here and see, okay, here's the link that I can go. This is going to be really messy. And there's other ways to deal with this too. There's some good libraries for dealing with HTML stuff. But it's much friendlier if you're working with an actual API. You can just go and grab that dictionary. Right? So I've got the data, and we can go through. So we don't care too much about the data and the times. Like the keys aren't all that helpful here, right? But if we want the items out of our dictionary, we can go through and get all of those out here. Or if we know they're all in one call data, because I know what this API looks like, right? We can say for my value in my data index of data. Seems a little silly, but that's okay, right? So this will be every item in the list. Then I can print that value. And I can go get out, okay, so here's all the things we got. So here's all the different coins: Bitcoin, Ether, Dogecoin, USD coin. This is the dumbest one. I don't know why people do these things. Shiba coin was another fun meme coin. Litecoin. Some of these sound familiar. I don't know a lot of them here. The graph. Any of these ringing bells? Anybody into cryptocurrency? No, I don't think it's Web 3.0. I think it's a big scam, but I'm a little weird sometimes, so. But it's fun. So we can go out and we can see, okay, here's what the supply is, right? Here's the current value of it here. Volume. What else is in here? Got a lot of data. Prices. Look at all that good stuff. That's a lot of junk here. Whew. Cool. So this is if we want to deal with getting information that's not on our computer, it's somewhere out in the cloud somewhere. Almost everyone has some sort of API you can go access. And not all of them are open that you can just go hit. Usually you need to have some sort of authentication. You'll add in some sort of code. And if you're dealing with that, I think we looked at the Marvel one, right? Is that the one we looked at? The Marvel API? I think I showed you this one. You can do it for free, and it just wants you to go get this key here. Once you have an API key, don't put that in your code. Right? That's a really bad thing to do, especially if then you're going to go commit stuff to GitHub. You don't want keys put into source control. That's a bad place for keys. So there's ways you can store keys locally and have them read out of things. That's a little bit more of an advanced topic here. But just a bad practice to put essentially passwords, right? A key is just like a password into your source control tool. It's not a great place for it. And then because this is a thing people do and people make mistakes all the time, there's tools people have built that go out and crawl public GitHub repositories looking for API keys. So there's a story, someone committed his Amazon API key by mistake. And by the time he woke up the next morning, he had $50,000 worth of charges from people Bitcoin mining. They're like, oh, here's a key, I can start spinning up instances. And they racked up $50,000 worth of charges. So Amazon's gotten a little bit smart to that, and they limit those sorts of things from happening now that they realize people do dumb things. But don't put your passwords in source control. Right? There's better places for it and other things to do here, but we don't really have the time to get into all those other fun libraries. But wanted to show you real quick so you can kind of go through and play with some of these things. It's a little bit bad that I've been like running this over and over and over just to show you, because every time I hit run, it actually goes out and hits this API. So depending on what the API is, sometimes you get so many free requests in an hour, sometimes you get whatever happens to be, or you pay per request, or there's all sorts of different things now. Twitter or X now wants people to pay to get data off of their API that used to be free, and all sorts of silly things like that. So actually sending it out just when I'm developing is a little bit bad. So it'd be better to do something like take all of this and put it in a file that I can play with just for my development purposes, right? I could hit this one time, dump it all to a file, and then I could go use that file when I'm trying to debug and play with it and go through and explore. So I'm not actually hitting the web API every single time. That'd be a little bit nicer. We looked at a little bit in the files chapter. You can just dump data with JSON, with the JSON dumps. So we can take all that and just dump it to a file, and then we could read the file if we wanted, as some options here. But just gives us a couple options. Didn't we look at, I thought we looked at that one with dumps, maybe not. All right, so wanted to show you that. That's a fun one here. The last couple topics we have, I didn't even open up Canvas, I forgot. We should check Zybooks though and see how we're doing, right? I forgot to do that. Okay, getting caught up here with some of the earlier ones. 69% of chapter 1, we're getting there. Still a little behind in some of these later chapters, but we've got some time. Again, I'll run this probably the end of this, what did they say, next week? I'll run it, just put in the score. It won't be your final score, but it'll give you a sense for where you're at there. And then I'll run it again after we do final presentations. So you've got up until then. On finals week, you have much better things to do than Zybooks. Right? I imagine you probably have other important things that are not going through the Zybooks. It's up to you how you want to schedule your time. So the last couple topics. Oh, I got to log in here. Did I forget? Thanks, Duo. Code 278. All right. We're just going to touch on some of these topics. Again, they're big things we get to next semester as well, when we start talking about inheritance and recursion, and then a little bit of fun for Python for data science. Using APIs will be a big thing when you're working with data, depending on how much data you're working with. Right? But usually we want to pull some sort of data. We're not going to have everything local, so it's pretty common to go get some data from elsewhere. Interacting with databases is another way. We don't do that in this class, but you get to it in other classes. But essentially, we've gotten through all of our course objectives. Pretty close. So look at requirements with UML, use case and activity diagrams. I think we drew a couple pictures with the diamonds. right? So that's our activity diagrams. The use cases is really silly. It's not worth spending a whole lot of time on. Some people really like them. Not some people think they're silly. I'm in the silly camp. But it's a way to draw out a picture of this is what the application should do. This is the use case for my program. So I should be able to open up an app on my phone and transfer money from one bank account to another. That's a use case. And you make a picture for that. Okay, we'll compare merits of alternative designs for programs intended to solve the same problem. Right? We've looked at different ways of solving things. Some are going to be objectively faster than others. Again, we'll get into that further later, but generally if it gets the job done, great. Things that are readable are good. Create test cases based on module pre and post conditions. I don't like calling them pre and post conditions. Some people go nuts for these things. A precondition is what must be true before you run your function, and a post condition is what must be true after you run your function. That's all. So we did all these test cases where we arranged all of our variables. We said, okay, hey, I'm going to have, here's my car, and here's how much gas it has, and after I'm done driving it, it should have this much gas. Right? We can make test cases for that, and we can do that in our code rather than writing them out on paper. I don't think writing them out on paper is very helpful. Right? I'd rather have it in code so I can run it, but it's going through that same idea. Decomposing a complicated problem into simpler sub-problems. My favorite term here, functional decomposition. Did anyone throw that out at Thanksgiving? Talk about, oh man, I'm so tired from all the functional decomposition, and just look at the crazy looks you get from family. I get crazy looks from people anyway, because I don't know why, but they're used to nonsense for me. How about process programs using our integrated programming environment? That's PyCharm. We hit run, and it runs, so we don't have to do it by hand. Systematically test and debug small programs. Did you test your code to make sure it works? This is not different. This is different than unit testing. This is, did you actually plug something in and see what you got back out? Right? Like we've been doing along. Debugging, getting rid of the bugs, making sure it actually does what it's supposed to. Right? Running stuff in debug mode, super helpful. You want to get familiar with that so we can see the values of our variables, so we can see what's going on in different places here. Trace algorithms for correctness using simple test cases. That was our simple test cases. If I plug this number in, I run my function, I get this back out. Right? We did those. We used a program to draw UML activity diagrams. I don't know if we actually drew them with a program. I trust if you can do this, you can probably figure out how to draw some pictures. And Visio's nice, but it's an expensive tool. There's a couple free ones online you can use. We'll use our symbolic debugger to assist in the process of identifying and removing defects from buggy algorithms. That's the debugger. And we should be able to step through our programs, do that. Write pre and post conditions as part of the process of documenting software modules. Yes, I believe you can. Again, I think these things are silly. My apologies. Write recursive procedures. We're going to do that this week, and that'll be part of our lab, writing a recursive procedure. Just some basic ones. Write small programs in Python which solve a data science problem. The solve a data science problem was a bit of a stretch. I think I admitted that when we started here, because it's our first semester. What I like to focus on is simulating things rather than figuring out the hard math, because I don't know the math of Monopoly. Right? I'd rather make a little simulation and just hit run and see what happens. Those sorts of things here. Oh, I found that link too. I posted that one, I think, in the Discord. Was it Stand Up Maths, I think, is the one who did the video. He does a lot of Python coding here and there, which is nice. And then design and implement functions with versatile behavior. Use loops to perform repeated but not independent tasks, and model and process data items with multiple values. Very cool. So I think we've hit all the things on the list that sounded like gibberish when we started. It's been a fun, 13 weeks in now? I could count, but that's okay. Feeling okay? We're just kind of wrapping up here. So we'll talk a little bit about inheritance, a little bit about recursion, and then we'll do a little more Python for data science. And then next week is work time. So we'll probably, we'll do the lab on recursion today. I don't think we need to do another lab next week. We'll leave lab time for project time as well. So if you wanted to partner up, let me know. I can get you shared access to your partner's repository. I think I did that for one pair. If you want to do it individually, that's cool too. It's not required. Next semester, you'll have to do it in pairs, because learning to work with a team is an important skill as well. And then our final project presentations in 16 days, believe it or not. We're coming up here. So 11:30, a little bit earlier than usual. That'll be fun. It's not too early, right? It's not the 8 a.m. Isn't there like an 8 to 11 block? That's awful. Who takes a test at 8 a.m.? Like we understand brain science like a little bit here, and I feel like we know people aren't really awake at 8 in the morning, despite copious amounts of coffee. I don't know. Okay, anyway, let's get to the last little bit here. So inheritance is nice. So this is a tool here. It's very useful in specific cases here, but it's not a tool we're going to use everywhere here. So it saves us some time when we design things that are similar. So we're familiar with the concept of inheritance. If you spend any time in biology class, you remember there's ways we categorize things in biology, and for some reason it's still in my head. You have the kingdom, the phylum, the class, the order, the family, the genus, and the species. I don't know why. I really should have better things in my head, but that stuck with me for some reason here. So everything that is in a family is related, right? But different sub things, genuses and species, have different traits, right? They share certain things at the family level, but then they become special and distinct, right, at the species level. So that's what inheritance does for us. It says, hey, at some level we share, we are the same. So we're all mammals, right? We share characteristics with other mammals here. But what makes humans different than gorillas, right, are things different, unique to our species. So we can do that with our code with inheritance. So we can save ourselves a little bit of time here. Let me do a new project here for this one. We'll call this one inheritance. I probably spelled, is it ANC? Inheritance? Ence? I can't spell ever. ANC, okay, ANC. So when we're writing classes here, this lets us make common attributes be shared so we don't have to reinvent the wheel, which is nice here. So we're going to write a class. We'll call this one, how about mammal? So the class for mammal, then we'll have an init method here. And mammals will have some certain attributes here. So maybe we have a, I shouldn't have done mammal. It's too early to do biology. So things that mammals have. So we have a sound that we make. Right? We make certain sounds, and we have maybe a height here. I don't know. We can go from there. And we'll say my self sound is the sound, and self height is the height here. And then maybe we do something like make noise, and we're just going to print self.sound. Nothing super interesting here. So we've got a class for mammal. Now, if I want to make other classes that are mammals but do special things, right? I want to make a version of mammal but make it special and make it do additional things here. I can write a class that inherits from mammal. So maybe we'll make a class for human then, and to say I want to inherit from mammal or be a mammal here, I'm going to put some parentheses and put mammal in the parentheses here. So as humans then are mammals. So inheritance creates an is-a relationship. It's not a has-a here. So like we have tools, we aren't tools, right? So we can make a class for human and they can have a list of tools, but it doesn't make them a tool. Right? So in here then, we'll define our init method. Now, once and there's a couple terms we can use for the class you inherit from. I like parent class and child class. So your parent class is mammal, human is the child class. Or you might say mammal is your base class and human is your derived class. You're derived from this base version here. Or your superclass is mammal and your subclass is human. Superclass is pretty common, and we're going to use the word super to refer to our superclass. But you get all sorts of different terms for it. I don't know why we like 3 different terms, but like anything in programming, there's 7 different ways to do anything here. So we come up with different terms. So if my superclass has an init method here and it needs a sound and height, I need to have a sound and height to provide to it here. Because what's going to happen is when my init method runs, it's going to also run my superclass init method here. So we'll say, okay, I need a sound, I need a height, and then maybe I have an eye color or something for humans. So I'm going to say super.init. I'm going to give it sound and height here. So this will run my superclass init method here, the main mammal here. So it goes to, here's my superclass, go and run its init method here, given sound and height, and I can say self.eyeColor is the eye color. Why is it still cranky here? I did it, didn't I? Call the supers missed. Did I spell it wrong? I spelled it wrong. Hang on. let's try the little helpful hint here. I missed the parentheses. Sorry, super parentheses dot init. We need extra parentheses, of course. Sure. All right. Then other things humans can do then. So humans then might smile. And we'll print smile. I don't know. Well, it's a bit of a stretch here with biology. I'm sorry here. And then maybe we'll make another class here then for gorilla. Gorilla then is a type of mammal, right? It is a mammal here. So we'll do the same idea here. And then what makes gorillas different here, maybe we'll have their fur color, right? I don't know, fur color. Is it fur or hair? Do you call gorillas furry or hairy? Probably not actually fur. Is it fur? I don't know. That's fine. Well, we can do that here. And then gorillas, we can have a method for climb or something here. Because gorillas like to climb things. And we'll print climb. Right? So we can do these things. Now, here is where PyCharm being really smart gets to be a little bit obnoxious. Because if you hover over climb, it says, hey, it may be static. You don't need to take every suggestion it gives you. Well, this is correct here, and it could be static. So when it's saying it could be static, it means you're not using self. That's all. But we don't need to make everything static. We'll talk more about that next semester and look at specific cases for that one as well. But now I can make different instances of gorillas and humans, or even just a generic mammal if I wanted here, and I can call all the methods with them. Now what's cool is if I go and make a human, so we'll say Eric is a human here. Eric says happy Monday is the sound I make. I'm 6 feet tall and my eye color is hazel. Sure. So we'll call that here. Now, because human inherited from mammal, it is a mammal, mammal is its superclass, we have this function called make noise. Human gets the make noise method here. So when I say Eric dot, I see all the different functions, right? And I see all the different attributes. So smile is part of the human class, it's telling me. Make noise comes from the mammal class. But because I am a mammal, I have all the things that mammal can do. I can call make noise, or I can say smile, I can do all those things here, but I don't get climb because I'm not a gorilla. Right? There is no climb because the human class doesn't have that function here. Okay? So this is a silly one with mammals. This gets to be a little bit easier if we go back to geometry, because geometry is pretty basic here. So if we look at a class like polygon here, and then we define an init method here that takes a number of sides here. So we'll say my self.number of sides is the number of sides. That's a polygon. And then we also want to have a side lengths list here. So the length of each side, right? Sure. And what I want to do here is I want to say for, I don't know, side in range number of sides. I'm going to take my self.sidelengths and I'm going to append a 0 because I don't know what it is so far, but I want to say, okay, if I have 7 sides, I'm going to go add 7 zeros because I don't know the length yet, but that will set up my list here so it's the right size. Okay, and then I can call set side length, given a side index here and the length, and we'll say here's my self.sidelengths at the side index. We'll set it to the length. Right? So I can make a polygon, and I can go say, okay, your side length number index 0 is 2, your side length index 1 is a 5, side length index whatever. Make some sort of polygon here, right? And then we can get something like the perimeter. Parameter, that sounds right. We're going to return the sum of self.sidelengths. Side lengths, right? Just sum them all together, that's a perimeter. Assuming it's a closed shape, I have no idea how you'd mathematically verify that. So we'll just pretend like we can figure it out here. Okay, then it's okay. This assumes it's a closed shape. Or can you have a perimeter of an open shape? I'm really bad at math. I don't know if you can or not. Would you have to count it twice then? I don't know. Anyway, so we can do that, right? So now we've got a basic polygon, right? And it can do some fun things. Then we could write a class like rectangle, right? That is a polygon. Now, rectangles are polygons. Now, this init method needs a number of sides here, but we know how many sides rectangles have, right? So what I can do then in my init method here for rectangle, I can say I want my super.init, I can say it has 4 sides. It doesn't have to be an argument or a parameter here. I can just say I know it's 4. Great, right? Now, the problem I'm going to have, though, is setting side lengths. If I can set index 0 and index 1 separately, it's going to mean I'm not really a rectangle, right? So remember, classes, when we encapsulate all their details, we want to protect the integrity of the class. We want to make sure we don't do bad things here. So what we want to do then is we can say we're going to also define the behavior for set side length here. So we're going to override the behavior. I'm going to let it do something different from my parent class. So you see you get this little @ sign here, or a little note here. I guess it's just a bullet here. It's saying, hey, it overrides polygon. So we're going to do something different than this here so that I maintain the integrity of my class, right? So what I can do then is I can say, hey, I want super.set side length. I want side index, actually here, let's go. So if my side index modulus 2 is, or we can just do that. So this is the silly shortcut, right? It means it's not 0, right? Because it's true. If anything other than 0 is true, 0 is false. So you'll see this a lot in Python. People think this is really clever. Rather than saying does not equal 0, right? You just don't have to put that in because it's redundant at that point here. So I can say, okay, if you gave me a 1 or a 3 here, then I can go through and I'll say superset side length of 1 and the length, and superset side length of 3 in the length. So if you give me 1 or 3, I'll change them both, right, to make sure I'm maintaining the integrity of my rectangle. If you try and set 1, I'm going to change both those sides on you here, right? And then the else case, then, right, if it wasn't 1 or 3, it must have been 0 and 2. We'll go change those to that length here. So I'm going to change the behavior of set side length here to make sure you can't do that. Then I can also, if I want, I can add more functions to make this easier for rectangles. I could have a function like set width here, given a width, right? So you don't have to tell me it's index 0 or index 1 or index 2 or index 3. You just know, hey, set width here. So we can say self.set side length, and we'll say widths are the 1s, right? And the width here. This will call my own set side length function with 1 and set those ones here. And we can define a set length here, given a length, and we'll do that. We'll call that one 0 maybe. Right? Maybe the lengths are evens, the widths are odds. Length, oh, and self, there we go. Length, th. Okay. So I can add more functions here to make this a little easier to use. And now because I'm a polygon, I still get the perimeter for free. Right? I'll be able to get the perimeter of a rectangle because Polygon knows how to do that, and I am a polygon. Right? The other thing I can do is I can define get area. Right? So I'm going to return self.side lengths, side lengths of 0 times self.side lengths of 1. Right? Length times width. So I can figure out my area here because I can get my side lengths. Now, the next thing we can do, and you can have basically unlimited levels of inheritance. There's some limit somewhere in the thousands, I feel like. Please don't ever try. It's just not going to make any sense here. You know, maybe 5 or 6, or well, depending on what we're doing here. When we talk about making custom exceptions, a custom exception inherits from exception. And you are an exception, but you're a custom type. So you can do that as well. So we'll make a class for square. And square then is a rectangle, right? And rectangle, why? I spelled square wrong. And rectangles are polygons. So square is a rectangle, and it is a polygon, because rectangle is a polygon. So we're just going one level deeper here. So init on this one here, and maybe for square, we just want the length here. Maybe you tell me what the length is right off the bat. Again, you don't have to, but we could add this in if we wanted here. We could do length and width with our rectangle as well if we wanted. That's just an option here. Or we could default them to 0 if we wanted. Right? We could take length and width and say maybe, hey, if you don't tell me, I'll set them to 0. Right? Either way, we're probably okay here. And then we'll call self.set side length of 0 to length, and self.set side length of 1 to width. Sure. We could do that if we wanted here. So we'll take a length here. So I need to call my superclass. If your superclass has arguments, we need to give them. Now these ones have defaults, so you don't have to, but this will work really well. So I can say super.init here. I'll give it length and length. And then the only thing I need to do now is I need to change the behavior of set side length, because this one is different here. So I need to change set side length. Define set side length. No matter what side index, I'm going to set all of them here. So I'm going to set, say, super.set side lengths of 0 to the length, and super set side length of 1 to the length. So if you change any of them, I change all of them, right? And because my rectangle class changes evens together and odds together, right, we'll do it this way here. But then I can also have a set length and a set width. I don't want those to be different, so I need to change the behavior of those, set length and set width. So this we're also going to call then self.set width given the length, and then super.set length to the length. Right. So we'll call our set width, and then we'll call our set length. Oh, this should be superclass, sorry. Set width and superclass set length. And then we'll do the same thing for set width. Feels like a lot of work here to do these. It's a little bit obnoxious to have to change the behaviors to make sure we don't do bad things. But we can change these behaviors. Now we don't need to redo area. It already works here. We don't need to redo perimeter. It already works here. So we've saved a little bit of typing here by sharing those common attributes. And you can do some really cool things with inheritance. The libraries are full of things with inheritance, especially with exceptions. We say exceptions are a given type and a given type and a given type, and they sort of nest in these things. We can group them together here. And lots of fun things. Next semester, the textbook loves using inheritance when we start building out some of our basic data structures, because we don't need to reinvent the wheel, which is really cool. So it lets you share a lot of behavior and not have to copy paste things here. But essentially we should now be able to go and make a bunch of squares or rectangles and do whatever we want here. So we can make a polygon, we can make a rectangle, we can make a square. So we'll say polygon, it's a polygon, and it has 7 sides here. Our rectangle is a rectangle, capital R rectangle, and it, I don't know, a 3 by 2, and then our square then is a square. Did I spell it wrong? Why does it not like it? Oh, I haven't used, okay, that's fine. Is, no, square, it's a square, I don't know, size 4, right? And I can print my polygon.get perimeter. I can print my rectangle.perimeter, perimeter, and I can print my square.perimeter. Now, the perimeter of polygon is going to be 0 because we never set any side lengths here. So maybe we should set a couple. Polygon.set side length. Set side length of 0 and 5. I'm not going to set them all here, but that's okay. Uh-oh. Recursion text pair? What? I don't know what I did here. Recursion text pair. I think something happened with a light bulb somewhere here. Not all those suggestions are helpful. All right, let's try that again. All right, there you go. We get our perimeters, right? So 5 was, we only had 5. This should be 10, right? Doubled here, and then 16. Cool. And then we should be able to get our areas as well if we wanted, right? We could print my rectangle.getArea or print my square.getArea. But there is no polygon get area, right? Because there is no get area function in Polygon, because we don't know how to define that, right? We can do those. Now, if we wanted, we could do something different. We could also make a triangle, right? Triangles could be polygons. They have 3 sides, and then we could figure out its area separately, right? We could do that. Other silly things you can do if you want, you can define something like get area here, and then you can raise an exception. There's a not implemented exception that you can raise. So this says anybody who wants to inherit from Polygon will have a function for get area, but Polygon doesn't know how to do it. So it's basically saying if you want to inherit from Polygon, you should go implement this thing. You should go write a function for get area, because we want all polygons to have one. This is not all that super helpful or common, especially in Python. In other languages, it's nice to put this sort of function in here because you can do other cool things. Because Python does its duck typing, if it looks like this, it sounds like that, it must be one of those types. They're not super strict about it here. Other languages, if you don't have a get area, where was it here? This one here, they get area at the top level. It's harder to add them at the lower levels. There's all sorts of silly things you could do here. But you can do that. So if we wanted to add triangle, we could add triangle. There's the formula for getting the area of a triangle if you just know the lengths. I have to go look it up every time, but you can do that, right? You don't have to use the 1/2 base times height, because I don't know how to calculate the height of a triangle, right? But that's okay. We could go through and do that exercise, but that's just the basics. We'll get more into this as we go. So derived classes, base class attributes, overriding, the is a versus have a, this mix-ins and multiple inheritances. Other languages don't let you do multiple inheritance. Python does. So you can say, hey, I'm a winged animal and a mammal. Just comma separate the classes you want to inherit from. This gets to be a little bit messy, because if both your parent classes or superclasses have the same function, when you call super dot and try and get that function, it's going to go to the first one that you listed and run that one. So it's hard to be kind of specific around which one you want. It gets to be a little bit weird. And they have this mix-in that says, hey, I'm going to have some behavior. Again, I might not have implemented it yet, right? They've got it here, but you don't add it in the mix-in. You would just raise that not implemented, but say, okay, if I'm driving or flying or hey, I'm going to be one of these types here. So semi is transport and driving, flying cars, transport and flying and driving. So it gives you access to these functions essentially and says, I'll write these functions. We'll do more with that one later. And then unit test, we've done this one already. So you go and show you, hey, how unit tests work, and they're fantastic. Unit tests are a type of test case. That's how we got all those cool behaviors already. It was just sort of magic for us when we did it here, and unit testing is fantastic. All right, we got those. The next little bit, so we got another half hour is recursive functions. So the first little bit of recursive functions. The simple definition is a function that calls itself. That makes it recursive. So the function will call itself. So we can write one. Let me do another one here for recursion. Project recursion. So I'm fond of the function factorial. So factorial of some n, right? This function is going to call itself. So what we're going to do is we're going to take our number and we're going to multiply it by our number minus 1. And the number minus 1, and the number minus 1, the number minus 1, the number minus 1, all the way on down here. So we can say, hey, if n is equal to 0, we return 1, because factorial of 0 is 1 for some reason. I don't know why, but apparently if this doesn't work, all math breaks, or something like that. So sure. If it's not that, then I'm going to return n times factorial of n minus 1. So when I call factorial, if we kind of think through what's going to happen here, if I say I want factorial of 5, 5 is not 0, so it's going to return 5 times factorial of 4. Factorial of 4 is going to run. It's not 0, so it's going to return 4 times factorial of 3. Factorial of 3, right? So we're going to get this add. I'm going to put a breakpoint here, and we're going to print factorial of 5. Oh, and run it in debug mode. Oops, there we go. So over in this bottom left section, we looked at this a little bit before. This is the stack here. So every time a function's called, it goes on the call stack. And you can see what the different values are as we go. So instead of stepping over, I want to step into now. So step into will run into the next call as we go here instead of stepping over. So now I'll see, hey, there's a call to factorial, and n is 4. And I'm going to step. Now I'm calling factorial, and n is 3, and step, and step. Now n is 2, and step, n is 1. So I see here my call stack, all these different values here where n was 5, n was 4, n was 3, n was 2, n was 1. I can see their values at each function call here. And then eventually, when I step now, I'll get, okay, it's 0. I'm going to return a 1. Now I finally start returning values. So each of these is just waiting to get the previous value returned. Right? It said, okay, I want n times whatever comes back from this function. So when n is 0, I'm finally going to return the 1. And that returns to 1 times 1, which returns to 2 times that, which returns to 3 times that, which returns to 4 times that, which returns to 5 times that. So it all builds up as we go, and eventually we'll get out our 120. Now, this is actually terribly inefficient here, because Python has to remember each of those function calls and remember all the variables at each function call. Right? It'd be much easier. So this is factorial recursive here. It'd be much easier to do this with just a loop, right? So you can just define factorial of n and say while n is greater than or equal to 1, right? We want to keep on doing something, right? We'll take our value equals 1, and we'll take value times equals n, and then n minus equals 1, and keep on going, keep on going, keep on going, keep on going, right? Eventually we'll return the value. Right? It's just a loop, right? We could go through here. We don't need to do all these function calls because now I'm not going to have to hold on to every different function call in the call stack. So some recursion is just a basic loop. Not all of it. That's just a quick example here. So that's one way we can use recursion quickly here. Now, it doesn't seem super helpful here, and I'd agree, but it gets us into the idea of what recursion is. So there's other times where recursive solutions are about the only way to do things. There's ways to work around it really difficultly. Essentially, anything you can do with recursion, you can do without recursion. But not everything you can do with recursion, or I'm sorry, without recursion can be done with recursion. It only has special cases here. But you've seen when we look at our folder lists, we say, hey, let me go open this in Explorer. Here's a bunch of different folders. How would I write some code to go through and find all the Python files in my GitHub folder? Because I don't know how many folders are inside of folders or inside of folders or inside of folders or inside of folders, right? I could go nuts and have folders inside of folders and as many as I wanted. So what recursion lets you do is say, okay, let me just open up this folder, and if it's a folder, let's do the same thing again. If it's a folder, open it up, look for files. If it's a folder, open it up, look for files. Eventually we'll get to where there are no more folders, and I can just say, okay, if I find a Python file, good. So we looked real briefly at that OS walks function that goes in and grabs me everything out. That's a recursive function. It eventually will go through every folder in that structure here and just go deeper and deeper and deeper and deeper. So the file system is really handy when working with recursion to navigate files, because I don't know how many times this is going to happen here. We're going to use lots of recursion next semester as well, where we use it to solve different things and manage data in our data structures. Works out really well for us here. There's another really common recursive function we'll look at. We call it binary search, which is the really fancy term for just look in the middle, right? So we're going to define a binary search given some list and the n here. And I'm going to find n in some list, or maybe we'll call it the value to find, right? That's easier. Value to find in some list. So this only works sorted lists. So you might say this is a precondition, that the list has to be sorted, right? So some list has to be sorted for binary search to work. Otherwise, it's not going to work for us here, right? So to call binary search, we're going to look in the middle. Is the value I'm trying to find in the middle here, like when we did the guessing game? You start in the middle, and then you've eliminated half. Then you have another half to eliminate, another half to eliminate. Eventually, we'll go find it here. So we can say, okay, great. Oh, we need, I'm sorry, the start index is 0, and the end index, I don't actually know what that is here. Shoot, start index and end index. We need a start and end. So where's the start, where's the end? Well, we'll get to easier ways to do this next semester, but for now we'll have to tell it start and end. So I can say, okay, well, I'm going to look in the middle, right? So let's add those two together, take half of that. So the index to search is my start index plus the end index divided by 2. And please, for the love of God, make sure you do order of operations and use your parentheses here so you don't divide the end index by 2 and then add. It's really easy to happen. I've done it before, but yeah, remember, we know how math works, right? And then I'll say, okay, if my sum list at the index to find, index to search, is equal to the value to find, we're going to return the index to search. I found it at this given index. If I didn't find it then, right, so if my sum list at the index to search is less than the value to find. So if the middle point is less than what I found, it means I have to be in the larger side. So I'm going to repeat this process here. So I'm going to return my binary search, given the sum list, given the value to find. Now my start index is going to be my index to search plus 1. Right? I already looked at this one, so start one more to the right, this way, right? Because I know you're bigger than me here, and my end index is still the same, right? And if I didn't do that, now I don't really need it. I don't need else's here, because if you returned, your function's done here. You return the binary search, given some list, given the value to find, given my start index stays the same here then, my end index is the index to search minus 1. Right? You must be in the left half, because if I'm not smaller than your value, it must be bigger than your value, so you have to be in the small half. Right? So you go to the small half or the big half. And we just keep cutting in half and half and half and half as we go. But eventually, we'll get to where these are the same value. Great, that's fine. But if they pass each other, because we've subtracted 1, we've gone too far. So I can check then. So either I'm going to find it, or I'm going to search a half, a half, a half. But I don't have a way of saying I haven't found it. It doesn't exist. Right? So when we're doing recursive solutions here, recursive functions, we need to make sure that it's going to end. So right now it won't end because it's going to keep subtracting, and now that we've passed it here, right, it's going to go over and over and over. Some list value defined. There we go. With the minus 1 and plus 1, so we need a way to make it stop. So we can check then, hey, if my start index is is greater than the end index, we're going to return -1. It wasn't found. And when we go to search for something, -1 means it's not found. Not found. Or we could raise an exception if you wanted, depending on which way you wanted to work with these. We were able to search lists before and try and find values, right? Okay, so we can check it. So we can make some list, so some numbers. So shout out some numbers for me here. Any numbers? 7? 18? 4? Give me 2 more. 12 and 22. Okay, cool. So now remember, this only works on a sorted list here, so I'll take some numbers and I'll call sort on it here. And I'm going to print the sum numbers, the binary search. And what value should we find? Should we find something that does exist? Maybe search for the 4. Here's my sum numbers. And we're going to find a 4. So we're going to try a case where it does work. So it should give me back index 0, right? Because once we sort this, that should be the first one here, right? We got to give it the start index, and then the end index is the length of some list, some numbers, -1, right? Because there is no index at the length, right? It's the length -1. Okay, so we should get back. Oh goodness, I forgot. This needs to be floor division, so we don't get halves, right? Floor divided by. Sorry, you can't use floats. There we go, try that again. And we get back index 0. So it seemed to work. So we can run it in debug mode, right, and watch it go through its steps here. We don't need factorial, so I'll continue. All right, so we got the binary search. We're going to step into our code. So some list, right, 4, 7, 12, 18, 22. The value defined is 4, starting at index 0 and then index 4. So the first one, then, we found our index to search is going to be 2, right, the middle here. And we're going to check, does it equal the middle? No, it doesn't equal that. Is it less than the value we're finding? Nope, it's greater than, right? So we need to be in the small half here. So now we're going to reset here. So let's step into, we're binary searching now from start index is 0 and index is 1. Right? So we take the halfway point of that, which is 0, as we're rounding down at this point, right? And it does match. We returned our index. So that one worked for us here. How about we do this for all of them here then? So we'll say for number in some numbers, we're going to print the binary search of that number. Some numbers, and then there we go. This one we want to be number. So we should get the index of each number here then, right? And maybe we'll print this as a formatted string. So we'll say number is at index, and then this will be the result of its return. We'll put as a formatted string. That looks a little bit ugly, but it's probably okay. And the parenthesis? No. There's the binary search. There's the end of that. There's the end of the string. There's the end of the parenthesis. It's a lot of syntax there, sorry. We'll try that. We get 4 is index 0, 7 is index 1, 12 is index 2, 18 is index 3, 22 is index 4. So it looks good so far, right? The last thing we want to try then is printing our binary search. Some numbers, let's a number that doesn't exist here, maybe 2, given 0, and I'm just put those in here, right? And we get back -1, right? It gave me back successfully. I didn't find it here. Eventually my start and end crossed, and I knew I stopped. So again, this doesn't need to be a recursive function here. We could just write this as a loop, right? But this is a pretty common recursive function here. right? We could build it as a loop instead and say, okay, while my indexes haven't crossed, let's do this, do this, do this, and then if they match, return. If not, I just change the value of start and end. And that's all we're kind of doing here. But it gets you into some of the basic recursive functions here. They've got countdown, yeah, searching. Oh, look at that, search. And we kept splitting the difference here. Look at that, the midpoints. Here's our finding values, the highs and lows, right? Sure. And eventually we'll go there. In a sorted list, hey, we did that one. Find in a sorted list here. All right. I really don't like printing to debug things. I would much rather use my debugger, but that's an option, right? You're welcome to use this print here. Hey, we found things or not found, and like printing each step of the way here. I'd rather not, but you can as well if you want. So you make recursive functions. So when we look at recursive functions, what makes it stop is known as the base case, right? We're taking a complex problem and we're trying to find a simple solution. So with base cases, we know the solution, right? So our base case for factorial was n is 0. I know the solution. Anything other than that is complex. I need to break it down, make it one step closer to the base case. Say, okay, well, I don't know what the answer is, but I know how to get closer to the base case. So, okay, I'll just do that with -1 and I'll approach the base case. So maybe this should be like less than or equal to 0. In case can you do factorial of a negative number? I don't know. So maybe it just breaks, or maybe we have a different, we'll do that. We'll add a little check. We can say, hey, if n is less than 0, raise a value error, n can't be negative. Right. Just to check here, because I don't know what they're going to give me here. All right, so our base case then, and then a complex case can be simplified. So if you can identify a base case, and if you can identify a way to simplify a complex case, to make it approach the base case, it might be possible to solve with recursion. So the factorial, yeah, we did factorial pretty quickly here, right? Factorial -1, pretty easy. Oh, look at that, they have 2, n is 1 or n is 0. I guess I didn't need the n is 1, but that's okay. So we've got our cases there. So other fun recursive math functions here are this Fibonacci. I love Fibonacci. This is a fun one here. So let's go down some lines. I don't even remember how to spell Fibonacci, so we'll just call it Fib. Is that okay? You give me the nth number. Do you remember Fibonacci? It's got a pretty simple Fibonacci. Oh, it's 2 C's. There we go. I can copy that in here. Fibonacci. So Fibonacci, then, the simple mathematical definition of it here is its value. If it's 0, the nth is 0 is 0. If nth is 1, it's 1. Otherwise, it's nth of n minus 1 plus nth of n minus 2. That's it. That's our solution. So we can do that real quick in our code here. We can say, hey, if nth is equal to 0 or nth is equal to 1, we're going to return, well, I'm sorry, no, if nth is 0, we return 0, maybe less than or equal to 0. I don't know. That's fine here. And then if nth is equal to 1, we return 1. Otherwise, we're going to return Fibonacci of nth minus 1 plus Fibonacci of nth minus 2. That's it. We've solved Fibonacci. It's a simple mathematical definition. We took it right off of Wikipedia here. I guess I should cite my source here. I don't know if anyone's going to complain about Fibonacci, but you know, why not? Did I not copy it? I didn't copy it. There we go. All right. We've got it here. So we can say for, I don't know, nth in range, let's do like 100 here. We'll print Fibonacci of nth here. Oh, it's going a little slow. Uh-oh. Maybe we'll do that as a formatted string here as well. Nth colon, and that one, Fibonacci of nth. This way we can see how far we're going along in here. So let's stop and restart here. It's going a little slow. Okay, 30, 34. Do you know why this might be slow? What's our base case? 0 or 1? So literally the only thing we're ever doing is eventually getting down to a 1 and adding that up. So when Fibonacci, I guess we should format that, right, as a, was it digits, right, with the comma separator? Is it comma D? Is that how we do that? Comma D? There we go, with our digit separator. So when we get into the millions here, we've literally added up, and we've called this Fibonacci function this many times. So my computer now has run the Fibonacci function 24 million times, 39 million times, where it's gotten down to 1 and added that together, right? Because Fibonacci of 7 is Fibonacci of 6 plus Fibonacci of 5. Right? This is fun to kind of sketch out here, because this is, should I use the whiteboard behind me? I don't like the whiteboard. I can draw on my computer. So fib of 7 is equal to fib of 6 plus fib of 5. Fib of 6 then is fib of 5 and fib of 4. This fib of 5 is 4 and 3. This one is 3 and 2. This one is 2 and 1. This one is 1 and 0. Right? This one is 1 and 0. Right? Eventually, all of these are getting down to fib of 1 or 0. Down, 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 down. So you have to run it that many times, over and over and over. So it's incredibly slow to run it 165 million times to add 1 together. 165 million times of 1 and 1 and 1 and 1 and 1 and 1 and 1. And if I were to run it in debug mode, I think I can pause. Yep. So debug mode has a cool pause option here. Let me continue. So while it's running, I think, don't I get a pause? Where's my console? What's happening here? Did I hit continue? Oh, continue. I don't, okay, sorry, continue. It was binary search. Now, okay, so now here's the console, and I can hit pause. Right? It will, I don't need a breakpoint. Most of the time our programs just finish, or it's waiting for some input here. So if I hit pause now, I can go see, can we pause? There it goes, and it finally paused, okay. Okay, so it finished that call. I wanted to see, let's step into, so at nth of 39 here, we can step in. Okay, I have to put it in here, sorry. We'll add the breakpoint. I want to show you how many calls get in the call stack here. It's not actually that many as you go, which is nice. So we'll step into, okay, now we're at 40. Should get to this one here in a second. Come on. Didn't I step in? It's not working. There it goes. We pause? No. We put the breakpoint here, and come on, step in, step in. Why? Okay. Why is it not working for me? Run the debug. Fibonacci. Okay, there we go. So step in. Now nth. Okay, nth is 1. We'll just continue these for a while here. We want bigger nths. 3, 4, 5. We'll keep on going. Here, let's do this. I'm going to cheat here. This is really ugly here, but it's okay. So if nth is equal to, we'll go like 30, print 30. And I'm going to put my breakpoint here, because I wanted to pause there. There, we'll get up to 30 in a second. All right, I thought 30 would be faster. I forgot. It's a little slower in debug mode too, because it has to track all of it. It runs a little faster without debug mode. Okay, now we got to 30. So now we're nth is 30, so I can step into, and over and over and over, 29, 28, 27, 26, 25, right? So we only get in calls in our call stack, right, up to n. But then when we come back to here, right, we resolved the first call of Fibonacci n-1, which is n-1, which is n-1, n-1, all the way down to 1. Then we get to n-2, which has to repeat. n-2 then will go n-1, 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 all the way down to 1. So it takes forever here rather than a simple loop. So recursion is great because it's simple here, but sometimes it's terribly inefficient, right? So we want to be careful using it. Depending on what our use case is, it can be very useful. Fibonacci is lots of fun for that one here. I think we've got that here. Yeah, recursive, here's Fibonacci, yep, easy. Now, this is counting how many times it ran. This will tell you here, right? How many steps it's going to take, sure. The greatest common divisor is actually a really cool recursive function. It could be a loop as well, but it's fun as recursion, right? If they equal, we found the greatest common divisor. Otherwise, we return, if it's smaller, right, return the smaller subtracted from the bigger, checking the two. You know, it's whatever that, whoever's formula it is here. Is that Euler? He did everything right. Euclid, the other E guy here. He came up with this idea for it here. So eventually Python will crap out on you and just give up if you have too many calls in the call stack here. So if we don't have a base case that we can reach here, it will just crash. I keep getting bad suggestions here. It'll just crash on us. So let me do this before Fibonacci here. We'll define infinite given n here, and we'll say print n, and then we'll call infinite n minus 1, and we'll go plus 1. So if I want to call infinite here, so if there's no way for this to end, right, if I don't have a base case here, eventually Python will crash on us here. Maximum recursion depth. You can only get so many calls in the call stack. It looks like it's about 1,000 or so. And you can actually tweak that. You can change that value in Python. I don't recommend it because you shouldn't have to, right? At that point, we've probably gone too far here. But you can do those sorts of things. Right. The other fun one, but we'll get to it next semester. I just wanted to give you an idea of where this is useful here, are other recursive solutions to problems, like the, was it 8? No, the Knight's Tour. So I like chess puzzles because math resources, here we go. So the idea, here, oh, here's the Wikipedia page, is how do you take a knight piece on a chessboard and have it hit all 64 squares without repeating a single square? So for us, we can solve this with a recursive solution. We say, okay, if I haven't gone on all 64 squares, let's try and move. All right, we'll try a jump somewhere, and then if we haven't hit all 64 squares, try a jump. And we'll eventually try every single possibility until we find a solution. That's known as backtracking, right? If I get stuck somewhere and I can't move, that wasn't good, we'll undo it here. So you can go through and see how it works here and go through the Knight's puzzle. So we'll solve the Knight's Tour puzzle, which is fun. You can solve mazes with backtracking recursion, or if you hit a dead end, you just back up and keep going to where you were before. And this is where recursion makes it easier than just trying to build a loop here, because trying to manage all the other things in a loop is a lot of extra work here. So there's the Tower of Hanoi. You guys heard of the Tower of Hanoi? It's that little puzzle with you can't put bigger disks on top of the smaller disks here. Python. So if we just look for a solution here, the Towers of Hanoi puzzle with recursion is 6 lines of code. Because it says, okay, to do that, if n is 1, done. I can move 1 disk. If I can't move 1 disk, how do I make a complex problem simpler? How do I approach the base case? Okay, well, I'm just going to flip the auxiliary and the destination, right? Moving 4 disks is hard, but moving 3 disks is easier. Oh, moving 3 disks is hard. Let's move 2 disks. Oh, 2 disks is hard. Let's move 1 disk. Okay, sure, I move 1 disk, right? Then I repeat, right, with it flipped again. So I can move a single disk from the source to the destination, right? Move 1 disk from A to C is moving disk 2 from A to B, moving 1 disk from C to B, right? So I have to put it back on top. So it shows you as we go through how to solve moving the 3 disks, right? If I want to get them all over to here, right, I can't move all of them at once, so I can simplify it. So a quick recursive solution here is just a couple lines of code. So this is Towers of Hanoi, Python, non-recursive. Recursive. We could ask the chatbot, I'm sure, too. Let's see. Oh, look at that. Bing AI is going to do it for us. Non-recursive solution. So to do it this way, you have to keep a list and keep track of all these things here and know which one we're moving here from where to where. That's a lot more complicated and a lot more brain power, right, than it is to just say, okay, let me do this -1, and then I'll repeat. So that's a fun recursive solution. All right, so we'll do some more recursive things in lab. We'll do some basic examples. We're not going to do anything too crazy here. Don't worry too much about it. And then that'll be our last lab exercise. Next lab, next week, will just be for project work time as well. So do keep in mind, you need 10 commits over this period of time before the final project, right? To make sure that you're spreading the work out to help you, to make sure you haven't just found a solution and copy pasted it in. It's really easy to tell when people take the first 10th and copy paste that in, and take the next 10th and copy paste it in, and take them. Right? I'm not stupid. I miss a lot of things here, but that one's really obvious, right? When I'm writing code, things change on different lines all the time when I find different bugs and things like that, or if I want to change things. So you can tell pretty quickly, right, that nothing else has changed. So please, just do the work. I promise you it's not that hard, right? Start with one little bit of the Monopoly game and get that part working, and then add the next bit, add the next bit, add the next bit. Save the save and loading for the end. Right? You don't want to start with that. Right? Save that bit for the end. So get the little bit working so I can move around the board, maybe get it where I can buy a property, or I have to pay some rent, or maybe now this player gets skipped if they have no money. Right? Take little steps. Take the big problem, break it down into smaller problems here. And I know you're allowed to work in pairs with the code, means you can share your code. But still, you're welcome to chat in English with everybody else in the class. Like, hey, what do you think? How would you go about this? And as long as you're not talking in Python, right? Share ideas. That's great. Okay, I think I'm going to go about it like this. Here, I will do this, and here's my ideas in English. That's great. A good way to collaborate with each other here. Totally welcome to do that. All right, so I'll see you over in lab in a couple minutes. Thanks, folks.